Hi, everybody, and welcome to our first, hopefully of many, Krembil Science Jams. So I read, actually, this is such a big deal that they were rerouting traffic. There's increased police presence. TTC has new lines. That wasn't for us? Oh. Yeah, so there's that other thing also going on. But here's what I'll say about Taylor Swift and us. Our team that makes this happen is better than Taylor Swift's team. So let me thank our comms team, led by Heather Sherman, who's sitting in the front row, and our entire Krembil team, led by Amy and Kim. Amy does not like to be pointed out, but she's right there. Thank you very much. This night is not possible without all of their amazing, amazing support. And certainly this night is not possible without all of you. So thank you for taking the time to come and hear about the exciting things that are going on at Krembil. So let's talk about why we're here today. So we're here because of patients like John. So this is John, and John has Parkinson's. Right now, we can improve his tremors, and you're going to hear about some of the ways that we do that. But we don't have a cure for Parkinson's. This is Olivia. And just based on the picture, you can tell Olivia likely has arthritis. And again, with arthritis, we can improve her mobility, but we cannot cure arthritis. This is someone you know and someone you love. They have dementia. We can make them more comfortable, but we cannot cure dementia. So one of the reasons we want you here is we want you to help us, our researchers, our clinicians, help us find cures. So we believe that without research, you can't have a cure. I can't guarantee you that research will get to a cure, but I can guarantee you if we don't do research, we'll never have a cure. So thank you for your support. We are touched and we are thrilled to be able to show you what we're doing. So let me turn it over to our host for the evening, the incomparable Mary Ito.
Should I use this one or? No, she needs that mic. I'm going to use this one. Wow, I've never been called incomparable. Thank you, JD, for that warm welcome. So welcome to the Un-Taylor Swift event tonight. True story. I've already told some of the staff here. I was waiting for my Uber tonight, and this young woman dressed in sequins and sparkles walked by me. So I went, hey, are you going to the big event tonight? And she's like, yes. I mean, she could barely contain herself. And I said, great, I'm going to the Krembil Brain event too. And she's like, what? And I said, it's okay. It's invitation only. Sorry. Maybe next year. Anyway, thank you, everyone, for coming out tonight. You are going to have an amazing time tonight. First off, I just want to ask you, how many of you hang out with researchers? And I mean for fun. Okay, for fun. Yeah, big difference. Okay, right? Oh, for fun. Oh, all the hands went down for fun. That's only me. Okay. I love hanging out with researchers. Okay, a lot of my friends are researchers. They're so much fun. I even married one. Where is he? My husband's at. There he is, Mr. Fun Guy in the back. Carlo. Yes. Anyway, researchers are fun people, right? They bowl, they go to movies, they dance, they sing. And, I was thinking about it, and I think another reason why I like researchers is because they're very much like journalists. Journalists and researchers do not accept things as they are. They look beneath the surface, they dig deep. They ask a lot of questions. And in the end, researchers and journalists are both searching for the truth about something. So I think we do have a lot in common, and they're also very passionate, as a good journalist would be, about what they do. And I think this is going to be in full evidence tonight when you hear from our amazing speakers. And they are going to be talking about some of the pioneering research that is going on right here at UHN's Krembil Research Institute. Just before we get started, I just want to go over a few housekeeping notes. Mundane, but most important, the bathrooms. Where are they? Does anyone know? You see? Oh, one person. Where are they? Very good. Yeah, because all of you will want to know that, all right? So let me just go over. Outside of this room, to the left, across from the doors where you all came in, okay? We also have a photo booth set up in the lobby, so please don't be shy. Go and get your photo taken with friends, your partner, your colleagues. And please make sure to post on social using the hashtags KrembilScienceJam and no research, no cure. I love that tagline, Jay Deep. I love it. You could write for Hallmark cards. It's such a great tagline. Okay, and you can also find our handles up there on the screen. Now, coming up, you are going to hear from 10 speakers tonight. Someone said, wow. I know your heart just sank. Yeah, because you're thinking, oh, great, 10 speakers. We're going to be here till midnight. No. Each speaker is only going to speak for 5 minutes. 5 minutes. Can you imagine putting your whole life, your whole work's passion into 5 minutes? Like, that is a heroic feat, but they've done it. So 5 minutes for each speaker. We're going to have the first 5. Then we're going to have a 15-minute break. You can go to the lobby, grab some coffee, treats. You can debate the pros and cons of deep brain stimulation, which I think I probably could use. Also get a quick photo at the photo booth. And then after the break, we're going to hear from the final 5 speakers. And then we're going to play a short trivia game, because who doesn't love trivia, to test your knowledge about what you heard. So please pay attention. The winner gets to spend an afternoon with Taylor Swift. You're right. No, that's not going to happen. Better. You get to spend the afternoon with one of the speakers of your choice, right? I mean, yeah. I mean, who wouldn't want that? Why would you want to spend an afternoon listening to someone's sob story about all the breakups that they went through? So, you will spend an afternoon with the researcher of your choice. You're going to tour their labs. You're going to meet their research teams. You will be so smart after that at the next social event, you will be saying, forget that cheese ball. I'm going to tell you about your ganglia. Yeah. Then you've got an opportunity later to meet and interact with the speakers outside in the lobby. That's a rare opportunity, right? Firsthand, so make sure you say hello to them and learn more about their work. Any questions? That's good, because we're on a tight schedule, so we're going to get right to it now. Our first speaker is Dr. Soumya Visvanathan. She is yes! Oh, big following, Soumya. Your fans. All right. She's a scientist at UHN's Schroeder Arthritis Institute, co-lead of the Schroeder Arthritis Advanced Therapeutics Center. She specializes in developing cell therapies and immunotherapies for the treatment of osteoarthritis. And on weekends, Dr. Visvanathan teaches Tamil, her mother tongue, to students. How wonderful is that? Okay, Soumya, you're up first.
Hello, everyone. Growing up, I used to watch my grandmother suffering with pain in her knee as she went about doing her household chores, never stopping, never complaining, but in pain. She had arthritis in her knee.
Her suffering never left me. Do you know someone in chronic pain? Maybe it's you. If you're female, you have a 1 in 4 chances of getting osteoarthritis, which is the most common form of arthritis. If you're active and have a knee injury, or if you're diabetic or you're overweight, you have a higher odds of getting arthritis. In fact, most people in this room will be impacted one way or another by this disease. Either you or someone close to you will get it. The concerning part of what I've just told you is that we have no cures. Right now, the best way to treat arthritis is to replace your joint with an artificial one. But in Canada, you typically have to wait till you're at the end stage of the disease. This could mean decades. Imagine living with pain as you're walking, as you're sitting, as you're driving, as you're going out with friends, going to work. And imagine the cost of living with this pain to you, to your family, to your employer, to the province. Now, if I tell you to think of arthritis, what comes to mind? If you thought cartilage, that's what most people think. In fact, for a long time, we thought of arthritis as a disease of just cartilage. My lab and others now recognize that arthritis is way more complex. It involves many different cell types. Focusing on cartilage was the old way of approaching arthritis. To find new cures, we need new ways of thinking. This is where I come in. I lead a team of scientists, students, engineers, and technicians, and we work very closely and collaboratively with clinicians to really understand this disease. What are the different cell types in the joints? How do they work together? Why do they stop working? We ask all kinds of questions to figure out what's wrong and to get ideas of how to fix them. We use this knowledge to develop new and exciting therapies. One of these therapies I'm going to talk to you about is called cell therapy. Cell therapy harnesses the power of the body cells to repair and regenerate itself. Think of your nails, or your skin, or your blood. If you get a cut or your nail breaks, it heals. But the cells in your joints have lost this capacity. But we can restart the repair process by putting in new cells into the joint, which have this ability. In fact, the experiments in my lab were so successful, we were able to start a trial in human patients with knee arthritis. We injected them with cell therapies, and most patients experienced a reduction in pain and an improvement in their symptoms that lasted up to 2 years. Think of that, just one injection. I'm now trying to move this research into the next phase of clinical trials where we can treat a larger number of patients and see if the effect is still working. Now, we did note that while most patients responded to the cells, not everyone did. There were some patients that responded better than others, the non-responders. And we're really trying to understand the biology behind the differences between the two. An alternate strategy that we're also pursuing is to use designer cells, designed so they work in the non-responders. We now have tools to engineer genes and proteins to enhance cells. Think of a computer back in the day and how large the processors were. Think of a computer now and how incredibly powerful and fast it is. Technology has really revolutionized computers, and we can do the same now with cells. We have the technology to engineer cells to enhance them and make them more powerful. But before we test these powerful enhanced cells in humans, we need to make sure they're safe and they're effective. We need real models to test them. Working with engineers, we developed a model of a knee that's arthritic, literally a knee on a chip. This is no small bioengineering feat. We can recreate flow through blood-like vessel networks. We can even add compression, like you would when you're sitting or bending your knee. We can add these and other stressors to mimic arthritis, and we can test our designer cells, our cell therapies, and in fact, all kinds of therapies in this model of a knee on a chip. I've told you about new ways of thinking, new therapies, and new technologies. I'm confident that with all of these scientific advances, we can finally crack the complexity of a disease like arthritis, so that people like my grandmother, people in this room, people in your family, your children, your grandchildren will suffer less. Thank you.
All right, Samya, I feel like we're on our way to the $6 Million Man. You remember that old show with Lee Majors? Question for you. You were saying that the injection of new cells, which is like astonishing that one injection could last 2 years with some people, but that it worked better in some people, but not in others. Why do you think that is, and how would that affect your research?
It's a great question, Mary, and it's something that we're doing in our lab all the time. We actually came up with not one, but like a whole list of reasons that separated the responders from non-responders. And like all good scientists, we now need to test this in more patients to prove that our theory is working, right? So we're doing larger clinical trials. And in fact, we've just got a new center for orthobiologics, which will help us move our research into clinical trials. So we're very excited about that opportunity. But top of that list was the quality of the cells. We found that patients, especially the older patients, their cells were just not that fit. So we've come up with lots of different solutions to engineer the cells to make them fitter. And we think if we can do that, we can really level the playing field and help with the arthritis.
Excellent. All right, thanks very much. Another round of applause. Okay, and our next speaker is Dr. Karun Singh. He's a senior scientist at UHN's Donald K. Johnson Eye Institute, and he studies developmental and adult brain and vision disorders using stem cells and genetic analysis. In his spare time, he enjoys watching cooking shows, which I find very interesting because I'm wondering how the two connect. You know, I don't know, does he mix up and measure stem cells and makes a recipe out of them? I don't know. But let us welcome Karun. You're up next.
Hello, everyone. Thank you for coming. It's very nice to be here. So as a kid growing up, I was really excited by Star Trek. Yes, I was a Trekkie. It's okay to say that, I think, because I am a scientist. And I was always enamored by the idea that I could have all the tools and technology that I would need. And I would be on one of those starships, Enterprise or Voyager, and exploring the unknown. Going out there and seeking out new life and trying to make new scientific discoveries and going where no one else has gone before. That attitude and that way of thinking is what we do in our lab every day. And we are very interested in studying the brain and eye and how cells connect to one another, how cells grow and change over time, but also how they degenerate in conditions like Alzheimer's or glaucoma. So what you see on the right, you might think it's a planet in a faraway galaxy, or maybe a supernova, a bursting star, but it's not. This is actually 3D engineered brain tissue that we make in the lab. Now, this technology is not available on Starship Enterprise, but let me tell you, it's super exciting, and I'm going to tell you about how we use it. So how do we generate it? Well, it actually starts with a very simple vial of blood, the same vial of blood that you would give at a doctor's office or at a blood lab. We get that vial of blood, it comes to our lab, and we can extract out the blood cells. And then we add genetic factors to those cells, and then what you get over time in the lab are stem cells. So those blood cells reprogram into stem cells that divide, and we can make millions of them in the lab. We can change up the growing conditions once more, and you can generate three-dimensional tissue. And so what you see on the right is a brain organoid. So this is generated in 3D in the lab, but from a blood sample, a simple blood sample. Now this is revolutionizing the way that we do research now, because we can now have someone's brain in a dish, or at least some version of it. The cells that we have in these organoids, they form connections with one another, they're electrically active, and they form neural circuits similar to what we're finding in the human brain. So I'd like to share with you how we kind of use this in the lab to study brain disease. So on the left, what you see here is a brain organoid. That's been engineered so that the brain cells are connected to one another, and it's the red cells connecting to the green cells. And this is generated from somebody who's healthy. And if we can do the same experiment from any disorder, so what you're seeing here on the right will be somebody who has a genetic form of epilepsy. And you don't need to be a scientist to see the difference here. There's many more cells and connections between them in this individual that has epilepsy versus the healthy condition. So what we're able to capture is something that might be happening in their brains, but in a dish, without ever having to touch their brains. It was very powerful. And in addition, this is not only personalized, because this is coming from the single person that we're interested in, but also we can screen drugs and therapies in the dish first, before we go back to the patient. So we hope to be able to go from the right side back to the left side. In addition, at Krembil, we are absolutely enamored by technology, and we have such privileges here that we have access to some of the latest technologies released this year in 2024. It's a very fancy name. It's called spatial transcriptomics, but really what it is a very fancy way to genetically fingerprint each cell in that organoid. So why do we need to do that? So basically what you see on the left side, it's a very, very thin slice of tissue that's been put onto a chip. And it's that chip that has the genetic fingerprinting technology. On the right side is a blow-up. And you can see that each of those circles represents a brain cell, and the color represents a different genetic signature. So this is important for two different reasons. One is, it tells you what the cell is. So if you're studying Alzheimer's disease, you need to know which cells might be dying, but also the why. Why is that cell dying? We need to know the molecular fingerprint of that cell, because only then you know that, can you actually develop a therapy to reverse it. So as you can see at Krembil, science and technology is moving forward at warp speed. We have everything that we need here to be able to be leaders in the world in this technology. We have amazing basic science labs, and we work very closely with our clinical partners who give us blood samples, tissue samples, and sometimes even doing research in the OR. So this connection is very, very important. In addition, we have such a unique patient population here. And this patient population not only comes to the clinic for care, but they want to actively participate in research. This is absolutely necessary and very unique about Krembil. And finally, we have links to pharma and biotech. Sometimes you need some help to take a finding that's in your lab and to accelerate the development towards a therapeutic. So pharma and industry can do that. And in fact, this unique combination that you see here, this is the exact same reason that I moved my lab from a different institution in 2020. It was a very stressful time, but I wanted to be here at Krembil because I knew something special was happening, and I wanted my lab to be a part of it. So as you can see, I'm super excited to be here at Krembil. I'm allowed to take risks every day in the research that I pursue, and I'm encouraged to do that so that I can do the science that no one else does, so that we can find cures to the different diseases that we study. Thank you very much.
So can I have some of those brain cells? Like, don't be selfish, right? You've got a lot of them.
We'll need your blood first.
That's okay. I'm ready to give it. This is like amazing to me. I can barely get my head around it. So I read somewhere that we have 86 billion of these brain cells. Is that true? Like around 86 billion?
Yeah.
And each one has...
Many more connections. But
Okay,
yes.
okay, right. And each one has this unique fingerprint,
Correct.
right, that has been identified. Like, what is the potential now that you can identify and fingerprint all these cells? Like, what are the implications of this for you?
So it's very big, and in fact, it's broader. So all the different disorders that you're going to hear about tonight, this technology, it's already here, and we're actually building around it at Krembil, and it's going to completely revolutionize how we study disease. We can do this for organoids, but we can also do this on primary tissue that we get from samples from individuals. So we can really understand the disease at the center of the disease. So that's the first thing that's going to be really exciting about this fingerprinting technology. The last thing that I'll say about is the idea that these organoids, they're not only good for studying disease in a dish, but we also think they're going to be useful for possibly replacing lost tissue. So in disorders where you lose tissue, like and brain cells are dying, like in Alzheimer's or Parkinson's, these organoids might be able to be a medicine, a cell therapy for that person, and it's personalized because we're generated from them. So it's very exciting.
Amazing. Thank you so much, Karan. Thank you. Karan Singh. All right. Moving on. Up next, we have Dr. Luka Milosevic, a scientist at UHN's Krembil Brain Institute and the co-director of the Center for Advancing Neurotechnological Innovation to Application, also known as CRANIA. That is a great acronym, CRANIA. Did you come up with that? Who came up? Oh, Luka came up with it. I love it. You do research and you name your own institute. Okay. Dr. Milosevic's research lies at the intersection of engineering and neuroscience. He uses electrophysiology, wow, machine learning, and computational modeling to study the human brain. And when he's not in the lab or operating room, you can find him on an off-the-beaten-path hiking adventure or playing hockey. Luca, you are up next.
Thanks very much for the kind introduction. So as mentioned, I'm Luka Milosevic. I'm a neuroscientist and an engineer here at the Krembil Institute, also a professor of biomedical engineering at the University of Toronto, and I work in the field of neurotechnology, where we are harnessing the power of bioelectricity to develop new brain circuit therapies. And hopefully that doesn't sound too far-fetched. I'm sure you're all very familiar with a cardiac pacemaker. Well, I work on a therapy that can be considered as sort of the brain equivalent to a cardiac pacemaker, and this therapy is called deep brain stimulation, or DBS. It's essentially a fully embedded system that involves a pacemaker in the chest that's used to deliver very low-intensity electrical impulses to particular areas of the brain that are implicated in disease. And in the same way that a cardiac pacemaker is used to correct irregularities in the heartbeat, our DBS devices are intended to correct or override irregularities in the electrical activity of brain circuits implicated in disorders like Parkinson's. And we happen to be one of the pioneering institutes of this therapy. So I am in the operating room for every surgery that we do here at the Toronto Western Hospital, just next door. So we do about 150 surgeries per year. We're the highest volume center in Canada and one of the highest volume centers in the world. And I'm involved in performing recordings of brain activity during surgery. So what you're about to see and hear is the activity of a single neuron in the brain of an individual with Parkinson's. Can't hear it, but you can see it. So the reason that we do these recordings is actually to help guide the placement of our electrodes. So I'm essentially trained as an interpreter, and I can pretty much help pinpoint exactly where we need to implant the electrode based on the language spoken by the neurons. So if you imagine yourself on a train traveling through Europe, if you had a sort of a well-trained ear, you'd probably be able to tell exactly what country you were in based on the language of passengers jumping on board the train. In the same way, in the operating room, we can tell exactly where we are in the brain based on the language spoken by the neurons. So we actually use this information then to make sure that we're implanting the electrode in the correct area of the brain, where we're going to sort of ensure that we get the best possible outcome for our patients. So when we find the right spot, we can essentially stop a person's tremor with just the press of a button, and this is what it looks like. Yeah, so it's an incredibly gratifying feeling to be involved just in this process. It's oftentimes a very emotional moment, especially for our courageous patients when they, experience this first moment of tremor freedom in possibly over a decade. So it's just incredible what we can do. We can have an immediate impact, but as Jaydeep said, we can stop a tremor, we can do a good job, but not necessarily a great job. So there's still lots of room for improvement. As mentioned, sort of this is my clinical role in the operating room, but I'm also a neuroscientist and an engineer. So I'm very motivated to make this therapy much, much better. And I'm privileged to be able to leverage the intraoperative environment and this incredible window of access to the human brain for research purposes, essentially. So one of the specialties of my lab involves the delivery of electrical stimulation while we're recording activity of individual neurons in the brain. And we do this to sort of better understand how DBS works and how precisely we're changing the neural circuit function, and then how these changes subsequently manifest a therapeutic benefit, which we can assess in real time in the operating room. So as I mentioned, and as you saw, it's a very remarkable therapy, but there's lots of room for improvement. And one of the main limitations I want to just kind of make you aware of is that the therapy currently relies on stimulation 24 hours a day. So it's not necessarily the most efficient in terms of battery usage, but as you might have noticed in the video also, as soon as you turn the stimulation off, the symptoms come right back. The other thing is that it doesn't really do anything to the underlying neurodegenerative processes of the disease, and in fact, the disease continues to worsen over time. So you're probably all familiar with the concept of neuroplasticity, or you've heard the term neuroplasticity before. So it's the incredible ability of our brain to essentially modify the strength of its connections in order to adapt to our environment or day-to-day needs. And what we've discovered is that we can actually use deep brain stimulation to rewire connections in the brain and to produce long-lasting neuroplastic changes. So this is pretty much changing, it's a paradigm shift in terms of how we're applying deep brain stimulation. So we've identified very specific pathways in the brain that are involved in regulating movement, that are underactive in the context of Parkinson's disease, and we've recently demonstrated that we can actually use very specific patterns of activity to enhance the strength of these connections. And this strengthening actually lasts a very long time, even after stimulation is stopped. And the best part is that we're finding that the therapeutic benefits of the therapy can also last for a very long time, even after stimulation is stopped. So we're actually making exciting progress towards actually fixing the underlying neural circuit problem instead of just sort of masking it. I want to just leave you with a final glimpse of the incredible capabilities of DBS. So this is an individual with a rather pronounced Parkinsonian gait disorder. And you can see in the video on the left that just in the amount of time it takes for her to turn around, she's able to make it down the hall and back in the video on the right with stimulation on. So what we're working on is new methods of stimulation, essentially to rewire connections in her brain and to enable her to do this even in the absence of stimulation. And we think that if we can retrain these important brain circuits, we'll not only be able to offer her the symptomatic benefit, but actually slow down the course of the disease as a whole. Thank you.
Oh my goodness, another amazing presentation. Thanks, Luca. So yeah, I think it was really stunning, not just seeing the woman, but also that hand, you know, and what happens, the tremor stops when DBS is turned on. I imagine that...
Attention, please. Second code blue, Cell Pavilion, third floor, MRI, room 515. Second code blue, Cell Pavilion, third floor, MRI, room 515. Second code blue, Cell
3 times.
Oh, 3 times. Okay.
MRI, room 515.
I find it disturbing that no doctors jumped up to go and help this person. I don't know, like, shouldn't somebody be going? Anyway, okay, so Luca, just going back, I'm really struck by the fact that you're doing, I don't know if you'd call it real-time research, but you're right there in the operating room, right? Which, and I don't think you've got all day in there. So how do you do that on-the-site research, and then you're building on that?
Yeah, certainly the major limitation of this type of work in the operating room is that we're very much limited in terms of time. Of course, we have to get the surgery underway and make sure that we finish in a timely manner. So I mean, at the end of the day, we can gather extremely important insights in the operating room. There's no other context and during surgery that we can record from these areas in the brain at this, spatial and temporal resolution. So we can gather really valuable neurophysiological and mechanistic insights in the operating room. Of course, these patients then end up getting chronically implanted with these devices. So if we want to test new paradigms, we can follow up with them outside of the operating room. We can assess time course of effects over the course of hours or days or months or years. But then the other thing is that in addition to being in the operating room 150 times a year, I have a preclinical lab upstairs here in the Krembil Discovery Tower. So we can actually take these initial insights in a person and then reverse translate them, and we can pretty much optimize our methodology in experimental models of Parkinson's disease, and then we can essentially bring them back to the clinic. So yeah, I mean, probably not too ambitious to say this maybe the only place in the world where we can take an insight in a person in one day, take it back to the lab the next day, and then bring it back to the clinical setting the very next day. So
Right.
we're very efficient, and we're not looking to make a breakthrough in a decade or in 2 decades, but hopefully a meaningful impact today.
Yeah, that's fantastic. All right, thanks so much.
Thank you.
Luca. Wow, okay, learning a lot today. I don't know about you, right? Lots to learn about today. Okay, On to our next speaker, Dr. Carmela Tattaglia, a clinician investigator and neurologist at UHN's Krembil Brain Institute and the Marion and Gerald Soloway Chair in Brain Injury and Concussion Research. She's also co-director of UHN's Memory Clinic and leads a new clinical research unit at Toronto Western Hospital. You're going to hear more about that. Dr. Tattaglia uses brain imaging and molecular analyses to better understand the causes of cognitive and behavioral dysfunction in neurodegenerative diseases such as Alzheimer's and other forms of dementia. And in her spare time, she enjoys running and the great outdoors. Carmela, you're up next.
Thank you. Thank you for having me, and thank you all for coming. I'm going to talk to you about something that I think is quite important, and maybe some of you will too. Imagine not only losing your memories, imagine losing the very essence of who you are, your personality, your emotions, your sense of self. Every thought and feeling is governed by the brain. This essential 3-pound organ controls everything, from the most simple task to the most complex human experiences. And although people often associate love with the heart, that will change because it's the brain that loves. And the brain defines you, and when your brain changes, you will change. In my lab, we try to understand these changes. Despite many advances in neuroscience, we know very little still about the brain. We're starting to learn how cells communicate. We're starting to understand how they generate memories and emotions, but we have so much more to discover. We are trying to understand how healthy brains differ from those with conditions like concussion, Alzheimer's, frontotemporal dementia. I'd like to start, however, by telling you a little bit or clarifying some things about dementia. So dementia is basically a constellation of symptoms that impact your daily life so much that you become dependent for the things that you used to be able to do on your own. It isn't really a diagnosis. It's actually an umbrella term that includes many different causes. Another thing about dementia that people sometimes don't realize is it doesn't only affect your memories. It can affect your language function, change your personality, give you symptoms like depression, anxiety. And lastly, although we think of dementia as a disease of the elderly, there are many people who have dementia who are in their 40s, 50s, 60s. Many have been misdiagnosed with depression or simply aging. And that misdiagnosis can lead to lost jobs as well as failed broken homes. So in my lab, maybe I've turned it off. Yeah, in my lab, we actually use clinical data with imaging, genetics, biofluids like your blood, your cerebrospinal fluid to make diagnoses, to uncover the multiple pathologies at play that are causing all of your symptoms. The hope is actually to be able to bring you personalized treatments. I think it's important to note that, these brain diseases, these neurodegenerative diseases, they actually begin in our brains decades before we show any signs of disease, actually, when the scans look completely normal. In my lab, we try to uncover these changes at very early stages. We try to understand how these multiple pathologies can live in the brain at the same time and interact with other processes like inflammation to damage the brain and cause the symptoms that we see. I also try to understand how repetitive head injuries can cause different neurodegenerative diseases, including that chronic traumatic encephalopathy that we have described in athletes. I look for commonalities and differences across the neurodegenerative diseases to try to find proteins and pathways that we could target so that we could modify the course of the disease. And that actually brings me to our very new clinical research unit at Toronto Western Hospital and the Krembil Research Institute, where it's not about making discoveries. Actually, we want to translate those discoveries to help patients, and that is what we do. We take the discoveries from the lab, we turn them into clinical interventions with the hope that we will be able to help patients. We take real-time biological information from patients, bring it back to the lab, and then design therapies that are very personalized with the hope that we will be able to alter the course of their disease. And you know, we're very fortunate at Krembil because we can leverage discoveries in other disciplines. So, you know, we can learn from arthritis, brain, vision, and cancer, and create new interventions. As well, we have new ways of looking for, you know, these, we can assess new therapeutics on a personalized level. People often ask me, how is it that you can work with people who have these terrible diseases? Well, they inspire me to work tirelessly towards finding a solution. We understand a lot more today, but we still have so much more to learn. We are now able to take, you've heard recently, to take people's fluids, create cells, create organoids, but as well in our everyday life as clinicians and as researchers, we can now intervene. Every breakthrough that we make brings us one step closer to ensuring that patients live long, healthy lives with their memories and personalities intact. Thank you.
Thanks so much, Carmela. This sounds very hopeful. And I'm just wondering, I mean, dementia is such a devastating disease. What are the chances that we are going to have better treatments in our lifetime?
I would say 100%. You know,
100%. I'm going to hold you to that.
100%. I work in a field where, you know, until a few years ago, we had only failures in Alzheimer's disease. We now have 2 drugs that are FDA approved to alter or modify the course of the disease in Alzheimer's. We today actually found out that it got approved in Europe, so we are waiting, holding our breath in Canada. I work with people who have rare genetic forms of dementia, and we have 8 clinical trials with gene-modifying therapies for these patients. So in my lifetime, I'm thinking 100%.
Wow. In my lifetime too, I hope.
Yes.
Okay. Thanks so much. Wow, that is amazing. You heard it here tonight. Okay, Dr. Josh Rosenblatt is our next speaker. He's a clinician investigator and psychiatrist at UHN's Krembil Brain Institute, specializing in treatments for mood disorders such as depression and bipolar disorder. Dr. Rosenblatt has a large clinical research program that investigates innovative treatments such as psilocybin and ketamine-assisted psychotherapy. Outside of work, he enjoys traveling and spending time with his family and dog. Thanks for making all the other researchers look so bad. Nobody mentioned family. No, they like taking cooking classes on their own, and they like going hiking on their own, but no, you like spending time with your family and your dog. Come on up.
Walk slow.
As a psychiatrist, I've had the privilege of meeting with thousands of patients and hearing their stories, hearing about their lives, families, hobbies, and what they hope their lives would look like. I also hear about their greatest fears, failures, and the worst moments of their lives. On a Thursday afternoon, I met with Jane, a mother of 2, referred to me for treatment recommendations for her depression. Jane was also a teacher, but had been on disability leave for the past 2 years. In my office, Jane opened up her backpack and one by one took out the various antidepressant medications she had tried, all of which were not helpful and had challenging side effects. Unfortunately, for patients that have tried a variety of antidepressants and are still not getting better, the likelihood of yet another standard antidepressant working is less than 10%. This disturbing statistic has haunted me since the beginning of my medical training. In every patient interaction, I can't stop thinking, we have to do better. These outcomes are unacceptable. This constant discontent with currently available treatments is what has driven me to dedicating my career to conducting clinical trials to find better treatments that may dramatically improve patient outcomes within our lifetime. One intervention we're studying in the lab is psilocybin, the active ingredient in magic mushrooms. Psilocybin creates an incredibly novel altered state of consciousness, sometimes called a psychedelic trip, that dramatically changes the way you view yourself and the world around you. We're learning that psilocybin encourages the brain to rewire itself in ways that may dramatically change the way that you process, think in more resilient, adaptive, and flexible ways for your thoughts and your behaviors. So what does it actually look like when participants are in our clinical trials? Pictured here, you can see one of our psilocybin dosing rooms at Krembil, just a few floors above where we're standing right now, actually just next to the clinical research unit. As you can see, it looks nothing like a standard hospital room. In our trials, we combine psilocybin with talk therapy. We believe that psilocybin may act as a catalyst to achieve breakthroughs in psychotherapy that may have not otherwise been possible due to the hardwired defense mechanisms that are commonly seen in depressed patients that prevent them from benefiting from therapies. We're conducting numerous clinical trials and starting to learn that psilocybin's benefits are likely far beyond just depression alone. Psilocybin and psychedelics more broadly have shown promising results for anxiety, depression, eating disorders, chronic pain, PTSD, and even bipolar disorder. With these benefits seen across such diverse conditions, we're starting to reconceptualize psilocybin not only as an antidepressant, but potentially as an antidistressant, with benefits for reducing distress and improving quality of life across diverse conditions. But we don't want to only understand what are the benefits of psilocybin, we want to understand how it works and what it could teach us about the fundamental underpinnings of how the brain processes pleasure, joy, happiness, suffering, and pain. For example, we're conducting studies where we conduct MRI brain scans before and after patients receive psilocybin so that we can learn how psilocybin changes the brain. We also have participants complete tasks while in the MRI brain scanner to see how their brain responds in real time to positive and negative emotional stimuli after receiving psilocybin. Beyond psilocybin, we're conducting numerous clinical trials with a variety of novel interventions. We're also working hard to better understand the biology of mental illness and conducting biomarker-based studies to better personalize care so that we can select the best treatment for you right at the beginning, rather than the current standard and error approach. I sincerely hope that these 3 lines of research will help Jane to get her life back. And I believe the ripple effects cannot be underestimated as Jane's students, husband, son, daughter, and other family members and friends would all benefit from Jane's recovery. I'm grateful that we can offer Jane a message of hope and the possibility of even participating in one of our psilocybin clinical trials to receive a treatment that is completely different from the standard of care. More broadly, we are reimagining what the standard of care for mental illness treatment looks like. At Krembil, insisting on better outcomes for mental illness is a top priority. And we're partnering with other experts in the field, such as the Center for Addiction and Mental Health, CAMH, so that together we can find better treatments for our patients. Thank you.
Thanks very much, Josh. So it sounds like there is incredible potential for psilocybin. I sort of have a 2-parter question. I'm wondering how helpful it can be for patients who are severely depressed and hard to treat. And then sort of the second part to that is, assuming that, though, it's not the cure-all for everything, what other kinds of interventions would you be studying?
Great question. So for the first part, definitely, that's actually the main group that we're studying it in severely depressed people that are particularly difficult to treat, sometimes that have tried dozens of medications. So it's certainly being studied in people with first episode depression, but also people that are severely treatment resistant and have tried everything under the sun. And it does seem to have some pretty promising effects in both categories. And you're right, no intervention works for everything, including psilocybin. So we are doing that biomarker-based research to try to better understand who's going to respond to which specific novel intervention, and we're studying a number of other novel interventions. One of our other largest programs is looking at ketamine, which is actually an anesthetic. And we use it at sub-anesthetic doses, so lower doses, and we're finding that it has some fairly promising benefits for things like depression, anxiety, and even personality disorders. So ketamine, psilocybin, and a number of other interventions we're studying because we're recognizing that it's not going to be a one-size-fits-all for something as heterogeneous and diverse as depression. Great question.
All right. Okay. Thanks so much, Josh
Thank you.
Rosenblatt. Thank you. All right. Okay, we are now going to take a very short break, about 15 minutes, so please go to the lobby, enjoy refreshments, have your photo taken, and then we'll see you back here. Thanks very much. Okay, I think we're good, right? We're all well hydrated. I was actually surprised that they're serving alcohol here tonight. Wow. I don't usually go to like late afternoon events where they serve alcohol. Good to know. I found out what code blue means. Yeah, it was just explained to me that code blue means not a good thing, cardiac arrest. Is that right, JD? Yeah, cardiac arrest. But I was very comforted by the fact that, because I was disturbed, right, that nobody got up here to go and help. But apparently, Olga explained to me that there is actually a code blue team. I didn't know that. So there's I guess it rotates and certain people get designated to be part of that code blue team. So when you hear code blue, then that team, rushes to the person who needs help. So I think we're all comforted by that fact. At least I am. Okay, welcome back. Our next speaker, we're going to get right to it, is Dr. Malad Lankarani, a scientist at UHN's Krembil Brain Institute, and his lab develops computational models of the brain and neurotechnologies with the potential to better understand, monitor, and treat diseases such as Parkinson's and epilepsy. And when he's not at work, Dr. Lankarani performs in a local Persian band. Is that not cool? He does not hang out with his family. No. He selfishly devotes himself to this Persian band called Razadel, which translates to Secret of the Heart. Let us welcome Malad.
Thanks for the introduction. It's really great honor for me to walk you through my research story. I'm a computational neuroscientist, and this means that I use math to understand brain and brain diseases. But you may be wondering how math is related to brain research. Let me explain. Imagine for a moment we stand at the edge of a vast, dense forest. Each tree in front of us represents a single neuron. There are 86 billion trees here. It's a huge number. This is the number of neurons in a human brain. And this forest is as intricate as it is expansive. The roots of each tree form thousands of connections with one another. And in our brain, this corresponds to thousands of trillions of connections between all these single neurons. And it is these delicate connections that allow us to think, to feel, and to move. I hope that I could share this feeling that our brain is very complex, and to better treat and detect brain diseases, we need somehow to make sense of this complexity. And math is a powerful tool to do that. Let me provide some context. One of the major challenges in neuroscience and in brain research in general is something we call a lack of observability. And it has two main elements. One is about missing data. Imagine we try to solve a puzzle with only having a few pieces. The second is about some hidden patterns of neural activities which are not readily observable. This is like trying to navigate in our forest without having any marked trail. In my lab, very high level, we develop algorithms and models that can fill in this missing data and can uncover these hidden patterns. Now, let me provide some examples related to brain diseases. One of the brain diseases that we are interested in is Parkinson's disease. And as you heard tonight, deep brain stimulation is one of the treatments. In deep brain stimulations, neurosurgeons put the electrode inside, deep in the brain, and these provide an opportunity to get access to neural activities of some neurons in a small area of a bigger brain network. We cannot simultaneously access to all the activities of the neurons in different regions because this information is missing. In my lab, to solve this issue, we develop models and algorithms that can combine information from different regions, put them together, and provide a system-level understanding of this brain network. And this understanding can help us to develop new strategies to treat patients. Another example of brain diseases that we are very interested in is epilepsy. In patients with epilepsy, there are some abnormal patterns of neural activities that trigger seizure. It is crucial and important to find where they are coming from. In some patients, we can find them. But most often, it's impossible. Why? Because these patterns are hidden. In my lab, we use mathematical models, combine them with artificial intelligence tools to uncover where these patterns are coming from and even predict when they will occur. The tools that we are creating are like GPS for the brain. They can bring these hidden patterns or missing data to light so that we can observe them. And if we can observe them, we can understand them. Now, I would like to expand on this and ask this question. If we can observe it, can we change it? Can we control it? Can we modify it? And this is where, of course, we use math for better understanding brain, but also we use it to develop new technologies, mostly related to neural implants and wearable devices to measure and modify brain activities. Honestly, I think we are at a very historic moment in science and technology because we can combine these mathematical models with artificial intelligence and neuromodulation techniques like deep brain stimulation to bridge the gap between neuroscience and engineering, between biology and technology. Let's go back to our forest. With mathematical models, we can have a deeper understanding of brain complexity. We can even develop new strategies and technologies to modify brain activities in cases of disease and injury. And as you can imagine, this is a big undertaking. I don't do it alone. At Krembil, I closely collaborate with neurologists, neurosurgeons, clinicians, and scientists, not only at UHN, but also at CAMH, at SickKids, at Krembil Center for Neuroinformatics. And I'm a part of a team called Krembil Computational Neuroscience Hub, or KCN Hub. We all come together, share ideas, and of course data, to have a better understanding about brain complexity. And let me finish with this fun concept in math that is called the concept of infinity or lack of limits. This is very well fitting to brain research. There are infinite ways to explore the brain and infinite opportunities for discovery. Thank you.
Thanks very much, Milad. Super exciting, especially when you said that we're at this historic moment when we are able to, I guess, close that gap between technology and biology. So what are you working on that you find particularly exciting in this area?
Well, I was not aware of Jaideep's first slide, but honestly, if you remember the story of John, who had Parkinson's disease. And then the reason I say Parkinson's because this is one of the major research that I'm interested in. But we can use technology to reduce symptoms, but not for cure. And then if we want to interpret what is the cure, at least my interpretation is that we can restore normal information processing in those brains. And one of the big limitations is that we cannot compare the neural activities of these patients with some people without these neurological disorders. Recently, I worked on a project in collaboration with Dr. Robert Chen that we actually developed a variable platform for recording neural activities and muscle activities, but together with a new stimulation technique, which is called focused ultrasound stimulation, and it is non-invasive. Why I'm saying it is very unique is because it is for the first time that we can actually non-invasively target some deep brain regions and record neural activities. And with this technology, I hope that we can actually do some comparison between neural activities between patients with Parkinson's disease and some other people who do not have any disorders. So this is what I think this can be actually bridging this gap.
Yeah, that's so exciting. And where's Dr. Chen?
Here,
Oh,
yes,
is he
at
here?
Krembil. Yes, yes.
But he's not here tonight.
Yeah, this is what I assumed that you're asking tonight.
Yeah, that,
No, Leslie,
he's
yes,
at home
Krembil.
having dinner with his family. Yeah. Thank you so much.
Thank you very much.
Very
Thank you.
exciting. All right. Our next speaker is Dr. Joan Wither, a senior scientist and rheumatologist at UHN's Schroeder Arthritis Institute. And her translational research focuses on systemic autoimmune rheumatic diseases, and those include lupus, Sjogren's disease, and scleroderma. Something a lot of people don't actually know about Dr. Wither, and I didn't know about this, is that she used to be a competitive gymnast, and she even competed in the Canada Games. Joan, I didn't know that. I'd like to see a triple backflip now and a double layout to the stage. Welcome, Joan.
Thank you for the opportunity to tell you about my research. I'm a clinician scientist, and that means I both see patients and I do research. In my research, I consider myself to be something of a science detective, performing experiments to obtain clues into the mysteries behind health and disease. The mystery that we're investigating is systemic autoimmune rheumatic diseases, or SARDs. These are conditions such as lupus that affect multiple tissues and in which the immune system attacks our body's own tissues instead of targeting infections. We don't really know what causes these conditions, and that's the mystery I'm trying to solve. Lupus affects 1 in 1,000 Canadians, including many young women. It can be a devastating disease, and it's complicated to treat because it varies in how it presents and how it changes over time. A number of patients have a relapsing and remitting course in which they have prolonged periods of low or mild symptoms that are interrupted with periods of increasing symptoms called flares. A flare can be as simple as having a skin rash or joint pain, but it can also be very severe with inflammation of the heart, the kidneys, or the brain. We don't know how to predict if and when flares will occur, but if we could do this and intervene, we could prevent much of the heartache associated with this condition. So imagine I'm in my clinic, and before me, I have 3 patients. All of them are 25-year-old women with a positive ANA or anti-nuclear antibody test. This is the gold standard test we use to make the diagnosis of these conditions. Patient number 1 has no symptoms. This is uncommon because 25% of women actually have a positive ANA test, and the vast majority of them will be completely healthy and never develop disease. Unfortunately, there's a small subset of these patients which will be asymptomatic patients in the early phase of lupus. With this patient, I would like to be able to predict who is going to go on to develop disease, and I would like to be able to intervene and prevent it. Patient number 2 has early onset lupus. This is manifested by a skin rash and joint pain. With her, I would like to know how severe is her disease going to become, and how likely is she to reflare in the next year. Patient number 3 has serious disease. She's admitted to hospital with kidney inflammation. We initiate treatment, but she fails to respond and develops impaired kidney function. In her case, we would have liked to be able to predict how severe her disease is and whether she'll respond to therapy at the time of her flare. In my lab, we do in-depth analysis of the immune system and immune cells, as well as the proteins they produce. And this has led us to appreciate that a set of molecules called interferons play a very important role in the immune disruption that occurs in these conditions. So going back to the clinic, how has this impacted patient care? Well, for people like patient 1, we've shown that in asymptomatic ANA positive women, a certain percentage of them have high levels of interferon, and those with the highest levels are at increased risk of progressing to disease over the next few years. And we've begun to obtain some very interesting insights into the immune mechanisms that lead to this transition. For patients like patient 2, we were the first people to show that high levels of interferon are associated with more severe disease. And we've also shown that one of the mechanisms by which this occurs is that interferon acts to promote the development of the immune cells that produce the tissue-damaging antibodies, and that the failure to normalize these immune cells with treatment results in recurrent flares. And finally, for patients like patient 3 with severe disease, we have begun to identify the immune profile that's associated with poor responses to treatment. What I find so rewarding about doing research is we get to solve, or try to solve, really important puzzles every day. As science becomes more complex, it becomes increasingly more collaborative, and together we have made some very important advancements. The pieces of the puzzle are coming together, and it's only a matter of time till this leads to early, more personalized therapy and better outcomes for our patients. Thank you.
Don't go anywhere yet. So Joan, I was interested that you said 1 in 1,000 Canadians is affected by lupus, right? And that many of these are young women. So why young women, and how would that play a role in your research?
So the ratio of women to men with lupus is 10-1. And this is because women have 2 X chromosomes, and that many immune genes are on the X chromosome, and we tend to have a higher response than men to various immune challenges. And also, sex hormones play a very important role in the immune system, and estrogens lead to enhanced responses. Both of these things cause women to make higher levels of autoantibodies and to develop lupus. And how does this impact our research? Well, we have to study both men and women, But we have to be sure that when we compare a healthy person with someone who has lupus, that they are matched for sex, or we might be identifying sex-related differences rather than disease-related differences.
Oh, wow. Okay, fascinating. Thank you so much. That's Joan Wither. I feel like I could go on and ask a million more questions, but I'm holding back. All right. Next up, we have Dr. Olga Rojas, an immunologist and scientist at UHN's Krembil Brain Institute, and her lab focuses on the role of intestinal immune cells in neuroinflammation and neurodegeneration, as well as the gut-brain axis. Now, this is so hot right now. I was actually just at the grocery store, and I saw on the cover of a health magazine, it said, "Your gut and inflammation," right? So a ton of people are interested in this. So this whole gut-brain axis is emerging as an important target in Alzheimer's disease. In her spare time, Dr. Rojas enjoys crocheting and knitting, two very civilized activities. And, oh, Josh, get this. She enjoys time spending with her daughter, who she calls her inspiration. Yeah. So there you go, one up on you, Josh, right? Her daughter, not just family time, her daughter is her inspiration. Please welcome Olga Rojas.
So hopefully I beat Taylor's dance tonight. And I passed the family exam, which are good ways to start. Thanks for being here today. Let me start with a question. Is there a connection between the gut and the brain? And if so, can we target the gut to treat brain diseases? This is a question that you all are having because we know that it's a hot topic. But let me tell you, this question didn't even cross my mind when I was working as a young physician back in my country, Colombia, treating patients with rotavirus, which is a pathogen in the gut. I never imagined that my curiosity regarding mechanisms of immune response against rotavirus will lead me to a career in science outside my country, and even better, here at Krembil. Today, I am a neuroimmunologist, and I am trying to understand the connection between the brain and the gut after brain injury. And we are trying to understand the role of the immune response after that brain injury. Neuroscientists always have been thinking about the brain as an isolated and independent organ. But we are learning now, with more and more evidence, that there is a really integrated relation between the gut, the body, and the brain. Whether it is through soluble proteins, cells, neurons, and even environmental triggers such as diet, we know that they are all interacting together and then communicating with the brain. And which is even more interesting is that we have the gut, and within the gut, we have viruses, bacteria, and parasites that are living with us all the time. They also talk with cells, neurons, with the diet, and later on, they go up to the brain and talk together. Fascinating, right? What is really important for us is that within the gut, there are really highly specialized immune cells. We call them regulatory B cells and T cells. And imagine they are like brakes in our cars, preventing from our engines from overheating. But what is really more interesting for me is that those gut immune cells can migrate to the brain. And not only into the brain, but also into the layers that covers the brain that we call the meninges. And they help to dampen the inflammation over there. We know that there is a fine balance between the gut and the brain. And when that balance shifts, whether it is because there is too much inflammation or not enough, that's when the problems in the brain starts. And that leads us to diseases such as neurodegenerative diseases, epilepsy, but maybe you haven't never thought that that connection between the brain and the gut will also lead us to other conditions such as obesity, or even anxiety or stress. Surprising, right? The other thing that is really important to highlight here is that this connection between the gut and the brain is what we call the gut-brain axis. All the cells are always interacting between the gut and the brain. And recently I discovered that during multiple sclerosis, some of those immune cells from the gut can migrate into the brain and into the meninges. But what is really more surprising is that this is a wide phenomenon that does not only occur in autoimmune diseases, but also in other diseases such as Alzheimer's disease and Parkinson's disease. And this is all the novel research that we are doing here at Krembil. So let me go back to our initial question. Is there a connection between the gut and the brain? And my answer is definitely yes. We know that there are gut-derived immune cells that are found in people with brain diseases. But perhaps a better question is how we can use all this information that I am presenting to you today to develop new understanding regarding how brain diseases develop and how we can create or develop new treatments for those diseases. So in my lab, we are doing really simple interventions to tackle this point. We are trying to change the composition of the gut microbiome and see if with that we can boost the immune cells to migrate into the brain. And even something even more simple is we are trying to change our diet. What if I tell you that what we eat will be important to boost our immune system in the gut to help us dampening inflammation in the brain? So far in our lab, we know that there are a few diets, like the ones that are enriched in fiber, for example, that help us to increase the amount of immune cells in the gut and favor them to migrate into the brain and the meninges during Alzheimer's disease. The more I understand and study the gut-brain axis, the more excited I get. But also, the more clear is to me that we need a holistic perspective to tackle brain diseases. Neuroscientists are trying to understand what is happening in the brain. My role is trying to understand what is happening in the brain from outside the brain. And what I love of being here at Krembil is the fact that, like immune cells, which come with different flavors, I am surrounded by amazing scientists. We have doctors, we have bioengineers, we have mathematicians, we have brilliant trainees working all together to solve big problems. And I am convinced that what we are doing will help us to develop new ideas, new approaches, and new treatments for brain diseases. Thank you so much.
Okay, that's like all amazing stuff. I have a feeling there's $1 million grant waiting for you somewhere. Yeah. So my question would be, what exactly is it about a good diet, right? What is it in that good diet that can help promote that migration of those helpful immune cells to the brain and then lessen the risk of brain disease?
Yeah, I think that's our goal question.
That's the $1 million question. Yeah.
So that's why I need the $1 million grant.
Okay.
So this is what I can tell you so far. It is an intricate relation. There are many, many variables working there. We already have a list of some factors that we do think can impact in a positive or in a negative way the boost of those immune cells in the gut. We not only want them to migrate into the brain, we also want them to produce soluble proteins that can maybe also go into the brain if they cannot migrate directly there. And within the diet, we already have some components from the diet that can help us to achieve that goal. In addition, the other thing that is interesting is trying to ask which are the components of the gut microbiome that maybe we can increase or decrease to have more of those helpful cells in the brain.
Right. Amazing. Okay, good luck with your work. Thank you so much, Olga. Okay, our next speaker is Dr. Nigel Haroon. He's the head of rheumatology at UHN, a senior scientist at UHN's Schroeder Arthritis Institute, and his research aims to better understand the immunology and genetic basis of axial spondyloarthritis. My whole evening was working towards saying those two words. Did I say that right? Axial spondyloarthritis, is that? Yes, okay, I got the thumbs up from Cleo. That is a type of arthritis that causes inflammation of the joints in the spine and pelvis. Dr. Haroon is also a celebrated wildlife photographer. He even had a photo published in National Geographic. Yes, 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 yes. And he also receives tonight's Best Dressed Researcher Award. Nigel, come forward. Yeah, big hand. Big hand for Nigel.
Thank you. Someone was commenting probably a tiger or some other picture might have been better. Anyway, thank you all for coming tonight and Mary for that kind introduction. Let me take you back a few years to my clinic room where I was waiting to see Andrew, a young triathlete, a dynamic person who was referred to me with a suspicion of arthritis. So the referral notes painted a picture of a successful businessman with a true passion for the outdoors and for physical activity. So that's the reason behind my surprise when I saw Andrew being wheeled in. Okay, yeah. So he looked much older than his stated age, visibly depressed and in significant pain. The pain was initially attributed to the significant amount of physical activity that he was engaged in. But soon, the pain would become overwhelming, and he was unable to walk or even take care of himself. He was eventually diagnosed with axial spondyloarthritis, or AS. For many, probably this is the first time you're hearing this term. AS is a chronic inflammatory arthritis that predominantly affects the spine. It affects 1 in 100 Canadians. A lot of these patients also have inflammation in the eyes, manifesting as iritis or uveitis, in the skin as psoriasis, and in the gut as Crohn's colitis. The relentless inflammation can lead to spinal fusion, resulting in chronic pain, lack of mobility, disability, and a progressive stooped posture. These chronic complications are not just limited to the musculoskeletal system. In a large population-based study involving nearly 25,000 AS patients and 100,000 controls done right here in Ontario, we identified for the first time a 60% increased risk of dying from strokes and a 35% increased risk of dying from heart attacks. Not only that, despite the availability of many advanced therapies these days, nearly 50% of these patients do not respond to treatment. This is because we don't truly understand the root cause of AS. AS is driven by a complex network of cells and molecules that it is very difficult to pinpoint exactly what is the root cause of disease progression. But here at the Krembil Research Institute and the Schroeder Arthritis Institute, we have the teams and the tools to tackle such big questions. Owing to our multidisciplinary approach, as others have alluded to, and the availability of advanced techniques, we can pursue high-risk, high-reward projects. And I'm proud, as the division head, to state that rheumatology in Toronto has been ranked #1 in North America for impact, publications, and yes, you can clap. Thank you. So one of the examples of high-throughput techniques that we use comes from single-cell sequencing. Our immune system contains numerous cells, some of which we know today, but many yet to be discovered. And each of these cells produce many, many molecules. It's not possible with traditional techniques to study each of these cells and the different permutations and combinations with the molecules they produce. So we have to rely on techniques like single-cell sequencing. That has really changed how we approach studies in immunology. With a small amount of blood and with a single experiment, you can actually get information on all the cells within that blood sample, as well as the molecules that they produce. So we can easily predict what the immunological makeup of a patient is, right, even before treatment starts. So with these cutting-edge technologies, we made a discovery, a new drug target. This is called MIF, or macrophage migration inhibitory factor. Now, this is a patent-pending discovery made right here at the Schroeder Arthritis Institute. MIF drives inflammation in all the target tissues that I mentioned earlier, the eyes, the skin, the spine, and joints in patients with spondyloarthritis. So we went ahead and blocked this molecule with a new inhibitor, a MIF inhibitor drug that actually reversed all of these manifestations in a preclinical model. Right now, we are working with a company in Austria to take this to clinical trials and benefit our patients with AS. So in rheumatology, we work with industry quite a bit, and we are now working with Novartis to bring CAR T-cell therapy to Canada for the first time. This will benefit patients with multisystem autoimmune diseases such as lupus, myositis, vasculitis, and systemic sclerosis. In another world-first discovery, we identified that the use of biologic medications, TNF inhibitor in this case, to reduce the risk of spinal fusion that I mentioned earlier by as much as 50%. This was a paradigm-changing discovery that has resulted in significant changes in the way we treat patients with AS. We also identified a window of opportunity that has led to an emphasis on early diagnosis and early treatment of these patients. So let's go back to Andrew. Andrew also faced a major decision. These were very early days, and we didn't know what the complications of biologic therapy would mean at that time. But he decided, he trusted in science and decided to go ahead with a biologic therapy, and in no time was he not just on his feet. You can see him completing his Ironman, and as of today, he has done 3 Ironmans already. And Mary, that's his family there, right by the side. What you see at the top middle is a full-page Globe and Mail article chronicling his story, as well as our discoveries in this space. So just like Andrew, we too need to take risk. We need to be bold. We need to invest. We need to push the boundaries of science so that we can help patients like Andrew reclaim their lives. And right here, Krembil Research Institute is the best place to do that. Thank you.
Thanks very much, Nigel. I actually like that picture where you talked about the complexity of disease and you had all those roads intersecting. I'm assuming that was Toronto traffic, right?
Before Taylor Swift.
Before Taylor Swift, okay. That story of Andrew is remarkable. Like, it almost seems miraculous. Like, is that a once-in-a-lifetime kind of story? Or, I mean, how often would you see something like that?
Very good question. You know, compared to what we were facing 2 decades ago, where we had just anti-inflammatories for treating these patients, absolutely the field has changed. We have so many options for treating patients. However, we still have major challenges. And as I showed in that picture, everybody's not an Andrew, right? So 50% of patients have excellent response. Another 20% will have a little bit of response, but still around 25% don't have a response. So you have to keep on trying to find the right drug for the right patient. So if only we had a good algorithm by which we could have predicted this right at the onset, we could have chosen the best drug for each patient. And then there are patients who will not respond to any treatment, and that's where the discovery is important. And hopefully, therapeutic agents like MIF inhibitors might change that as well. Thank you.
But I'm surprised. Sorry. You said 50% have an excellent response?
50% have an excellent response, yeah.
So then it's not uncommon for someone to actually make a dramatic improvement.
Absolutely.
Wow.
Absolutely.
Okay. Thank you very much,
Thank you.
Nigel.
Thank you.
Very inspirational. Okay. Our final speaker this evening is Dr. Jeremy Sivak, a senior scientist and the Graham Trope Glaucoma Research Chair at UHN's Donald K. Johnson Eye Institute. Dr. Sivak's research program examines the mechanisms of cell injury and repair in the retina with the goal of designing new treatments and drug delivery strategies. He's also a very talented jazz musician. Ooh, big challenge there for our other researcher. Maybe you guys could get together. Right? Yeah, you could play music together. And Dr. Sivak even builds his own guitars. Welcome, Jeremy.
I love that song, and I love music, but I think most people here would say that it's actually their sight that is their most important sense. We use it to navigate the world, we stare obsessively at our phones, and it's intimately associated with our most important memories. And I'm sure many people here can quickly recall a trip, like an iconic image from a trip or a family gathering. I'm showing you here a picture from a few months ago when my lab, my wonderful, fantastic research team, presented me with a surprise gift. But our visual system is also quite fragile. And a lot of people struggle with often irreversible and progressive loss of their visual function. For example, the common disease glaucoma, which often results in the loss of peripheral vision, like I've tried to simulate here. Understanding and addressing this problem is a major focus of my research. So what's going on? Well, the eye, as some of you may know, collects visual information, bouncing off objects in the environment around us, focuses it through the cornea and the lens onto light-sensitive neural tissue at the back of the eye that we call the retina. But this is only the first part of a cascade for us to be able to see. If we think of the eye like a camera collecting the visual information, then the next step is all of that information has to be collected and sent down a cable, what we call the optic nerve, to a computer, the brain, that processes and interprets that image. So a defect anywhere along this cascade can and does cause loss of sight. But one area that's particularly vulnerable is the place where that cable connects to the eye. If there's a defect or some damage there, then the eye might still be collecting that visual information, but it can't reach the brain, hence the loss of sight. And that's essentially what happens in this disease, glaucoma, which is a leading cause of blindness and vision loss, affecting nearly 100 million people worldwide and over 500,000 people in Canada. It is very much a neurodegenerative disease, and I've put up here a wonderful image from the Donald K. Johnson Eye Institute's clinical side of a patient's retina and optic nerve in which the degenerating fibers are outlined in red. Although it is often associated with increased pressure in the eye, and some of you may remember getting an eye exam with an air puff test, that's what it's testing for, is increased pressure, but the actual underlying molecular and biochemical causes of this disease are very much unclear. And unfortunately, like most other neurodegenerative diseases, there is no neuroprotective treatment and there's no cure. So how is my lab trying to address this? Well, I have a background, I spent a few years in the pharmaceutical industry, and I'm interested in medicines that address the underlying root causes of disease, and not just alleviate symptoms, just as another callback to the slide that JD put up at the very beginning, but with respect to visual function. And so I'm very familiar with this fairly well-established pipeline or pathway of drug discovery that is very difficult and challenging. And we are interested in pushing some of our discoveries along this pathway, but often the most challenging, the most uncertain, and the most creative part of this process is the first part. And that is the idea or the step of understanding a disease process better in order to identify new targets that would interfere with that disease process. And an institute that is a research hospital like this one is ideally poised to make those kinds of discoveries. So at this kind of institute, my lab team and myself are free to interact with and collaborate with basic, or I prefer the term fundamental scientists, there's nothing basic about it, and clinical scientists, whoever we need to, including some of the other speakers that you've seen earlier today, to push new platforms and new technologies, create new technologies, whatever we need to do to advance the project. And so what our lab does really is set up our own mini pipeline of research platforms. We study disease mechanisms by profiling tissues. So For example, in this case, I'm showing you a slice of human optic nerve and retina in which each colored pixel represents the activities of 20,000 different genes that we can separate out in terms of their functions and try to understand the chemical signals in which all those cells are talking to each other. Then we try to boil all that information down into new insights into what's going on in the disease process. And here I'm showing you some retinal neurons that have been treated with a molecule that we discovered that helps protect them from different types of injury. And then finally, we try to go back into preclinical models of disease and generate proof of principle that these molecules, or that this approach would work to treat the underlying disease mechanism. So in this case, this is a graph of declining retinal function with a solid line, and where we've treated with this molecule in the shaded area, that declining line has been stopped with the dotted line. So with this strategy, I'm optimistic that our approach has developed and uncovered new targets that I'm really excited about, that have the potential to prevent vision loss in patients. And also because of that brain-eye connection that I talked about, we believe that a lot of these targets may be relevant to other neurodegenerative processes as well. Thank you so much.
Thanks very much, Jeremy. So I'm curious to know, what would be one very important discovery in glaucoma research that you are working towards?
Thank you so much for that question. So I mentioned that it's a complex disease, and it's so complex that I think a lot of experts would call it an umbrella term for a collection of different types of diseases that all end in the same spot. I think this is often the case in pathobiology, the biology of diseases. And so what, to me, is a holy grail is to discover the first common incident or cause of damage that all of these different subtypes all experience, because that's what you would want to go after so that you could actually treat all the patients. So anyone who has this disease, this cure or this treatment would be effective for. So that, to me, is the key. And for what it's worth, my money and a lot of our lab research effort is looking at the neuroinflammatory signals that happen early in this disease process, which is what we think is one of the earliest events that happens.
Great. Thanks very much. Jeremy Sivak, thank you. Okay, so that concludes all our speakers. Can we have another big round of applause for them? Right? Yeah. I mean, in addition to, their research and their teaching and their clinics, and they had to make time to put together these presentations, right, and work on them, and that's no small feat. So we all really appreciate that. So now I'm going to ask the researchers to go out in the lobby, and you can sort of prepare your areas and whatever so that when people come out, they can go and speak to you. In the meantime, just for a few minutes, we're going to have a little more fun right now. We're going to play a game. This is the game I was telling you about earlier. The winner or winners will be able to cash in on that personal tour with one of the researchers of your choice. Okay, so you got 10 to choose from. Who here has played Kahoot? Anyone played Kahoot? Okay, it's a lot of fun. I've played it a number of times. It's really fun, and it's simple. This is going to be like 5 minutes. So what I want you to do is take your phone out. You need your phone, all right? And scan the QR code on the slide. Okay, you see there's a QR code. So you just scan that to play. Okay, just add that code that you see on the screen there. And then what you need to do is add your name. You will see there's a prompt. Add your name to Kahoot. And use your first name and your last initial so that we can identify you. You just need to use your first name and your last initial. All right? I'm sorry? Yeah. Okay, so hopefully most of you have done that. Let me just tell you, it goes very fast. You've got 5 seconds to read the question, 15 seconds to answer. Now what you need to do though is, you need to follow the screen. Okay, not your phone. Follow the screen. It will give you the question and the multiple choice answers. Then look to your phone and answer the question by choosing the right color. Okay, so you're going to see 4 different colors. You just press it on your phone, but follow the questions and the answers on the screen. Okay, are we ready? It looks like, yeah, pretty much everyone's ready. Okay, let's play. Tense up, everyone. Here we go. Choose your answer there. Oh, all right. We got 41 answers so far. Approximately how many deep brain stimulation surgeries are performed at Krembil Brain Institute annually? Gosh, that's a tough question. Blue, the answer. 150. Is that right? What? No, 40. Wait a minute. 150 is the answer. Yeah, 150. Okay, so the blue one. Okay, next one. Oh, scoreboard already. Oh my goodness. We have a tie right now. Kevin F. and Alexandra W. Okay. Right. Next one. Which of the following is not a systemic autoimmune rheumatic disease, or SARD? Okay. Which of the following is not a systemic autoimmune rheumatic disease? You've got 4 choices again. Five seconds to go. 48 answers. Oh, the answer is the green one, diabetes. Diabetes. Okay. Let's see who got that right. Oh, Kevin falls to second place. Barbara's up. Okay, Barbara. How did she get 1918? Anyway, okay. Which of the following is false about dementia? Which of the following is false about dementia? Well, these are kind of tricky. Okay, 3 seconds. The answer is, it only affects people over the age of 65. That is false. Oh, Preya now, in the lead. Vera second, Megan third. Okay. Which nerve is damaged in glaucoma? Which nerve is damaged in glaucoma? 15 seconds. Okay, I'm not even going to pick the green one because I can't even pronounce it. I don't even know what that is. Optic nerve. Optic nerve. 32 people were paying attention. Okay. I like that. Oh, Vera. This keeps changing. Vera's in number 1, and Preya's now second. Oh, poor Kevin is third. Okay. What is an organoid? An organoid. 15 seconds. What is an organoid? Few people are very puzzled by that one. Okay. An organoid is a small model of a brain grown in a lab. A small model of a brain grown in a lab, which we all want, right? We all want that. Yeah. Okay. Oh, Vera's holding on. First place. Kevin's now bumped up to second. He's fighting for this. Preya is third. Okay. Next question. Which joint or joints are most affected in axial spondylitis? I got to say that again. Axial spondylitis. All right? Which joint or joints are most affected in axial spondylitis? 5 seconds. Got a lot of answers for this one. The spine or pelvis. Spine or pelvis. Oh, Vera's still up there. All right. Holding strong, Vera. Kevin's close behind. Which of the following research techniques are employed at Krembil Research Institute? Which of the following research techniques are employed at Krembil Research Institute? Okay, winding down. Yes, all of the above. Genomics, molecular analysis, stem cell technology, all of the above. All right. Vera. Vera must be very quick with that button. Yeah, I'm sure she is. And Kevin. It's a battle of those two. Whoa, no, Preya's third, Barbara, and then Elisa. Okay. Which of the following is or are not active in our gut and influence our brain? Which of the following not active in our gut and influences our brain? Do you remember this one? 3 seconds. Oh, the answer, synovial fluid. Synovial fluid. Wow, who got that? Who got that correct? Let me just see here. Oh, Vera. Where's Val? Poor Vera. Kevin's back up. Kevin, what a fighter, honestly. Elisa, Sadie. What the heck happened to Vera? She just totally went off the scoreboard. Okay. Kevin's leading. Which technology or technique acquires brain signals, analyzes them, and translates them into commands? Which technology or technique acquires brain signals, analyzes them, and translates them into commands? Yeah, that's a tough one. Okay, let's see how we do. Oh, brain-computer interface. Brain-computer interface. Oh, we got a smart bunch of people here. Oh, Kevin. Kevin's still in the lead. Sadie, Michelle, and a non-existent Vera. Yeah, Vera's not even making the scoreboard. Oh, what is psilocybin? Okay, you got to get this. Okay, I don't want to see anyone not get this. What is psilocybin? Right? Think back, folks. I'm sure some of you know it intimately. Psilocybin, right? Magic mushrooms. Come on. Oh, did I just give the answer? Oh, good. Okay, a psychedelic compound found in some mushrooms. A psychedelic compound found in some mushrooms. Okay, Kevin's still leading. Wow. I'm sure there must be some people going, sign me up for that study. Sign me up. Okay. Bonus question. Which year was Toronto Western Research Institute renamed to Krembil Research Institute? Okay, that was not discussed tonight. That did not come up. Let's just see. Which year was Toronto Western Research Institute renamed to Krembil Research Institute? 5 seconds. I don't know. Your guess is as good as mine. Oh, wow. 2015. 2015. Okay. Well, let's see who won. Third place, Kevin. Kevin, congratulations, Kevin. Sadie, second place. Sadie. And first place? Oh, Michelle. Oh, Michelle. She comes from behind. Wow, I love it. The dark horse, Michelle. Michelle, wait, Michelle. Michelle, way to go. Michelle, so you need to go see a Krembil person to get your prize, well, to choose your prize of which researcher. You even get to take the researcher home. No, sorry. Okay, all right, so that is it for this part of the evening. We want everyone to head out, though, and say hello to our researchers. Thank you. Thank you to everyone who came out tonight. Also, a big thank you to our donors and supporters. I also want to thank the Krembil team, and especially a big thank you to Heather Sherman, who always keeps me in line and keeps me organized. Thank you so much, Heather and her team. All right, please go out and meet your speakers, get another photo, have a drink, and have a great evening and a safe home drive or walk or whatever. Sorry? Oh, and your gift pack. you get a gift bag. So don't forget to pick that up as well. All right, thanks very much, everyone. Thank you.